The security challenges in operational technology systems such as SCADA used in industrial environments like water districts are many. In traditional setups, sensors collect data and programmable logic controllers process the information and control actuators like pumps. SCADA systems, typically involving protocols like Modbus, facilitate communication between the PLCs and the central systems. However, older systems lacked robust authentication, enabling unauthorized users to manipulate devices if they mimicked legitimate systems. This vulnerability was less of an issue in air-gapped environments, but with remote access, this has increased the security risk. Then there's human-machine interfaces, which provide visual representations of system data and allow interaction, such as adjusting set points. With growing importance of data, especially for AI and analytics, improper access control can lead to increased security threats. The need for manual systems in case of a cyber incident is also a problem, with regulations like the American Water Infrastructure Act of 2018 emphasizing system resilience. This is a story about the importance of common-sense security measures such as multi-factor authentication and unique credentials for embedded systems to reduce vulnerabilities and defend against opportunist cyber attacks. I'm Robert Famosi. This is Error Code.
My name is Mauritz Botha. I'm the CTO of a company called XiO Incorporated, and we specialize on data platforms in the OT space.
Tell me a little bit about the old architectures. How were the KPIs collected back in the past?
Typically, what people had is when you have your sensors measuring everything, you've got your actuators like the switches starting everything and controlling, say, the speed of a pump. You typically put a PLC to read the values from the sensors, do some control logic, and then actuate what needs to be actuated. And then they would have a SCADA computer. So it is an on-premise server sitting there collecting the information, interacting with the SCADA system using a protocol typically called Modbus. There are some more modern incarnations like the Siemens protocols and the Allen Bradley protocols, but they all had one thing in common at the time at least, and that was it's typically a master-slave scenario. So the SCADA system, the SCADA computer is the master. It will send a request to the PLC saying, give me whatever piece of information. It will do something and perform some supervisory action like run the pump right now, in which case it will also send a command and the device will respond. And right there was the crucial thing, because the old protocols didn't have any authorization or any authentication. So if anybody could mimic to be the server on the network, they could also send the commands. And it wasn't a big deal because for the longest time, people had air-gapped systems. And what we saw, especially after COVID, is people wanted remote access. And with the remote access, the old model of having physical security where you have, say, a car tag on the outside of your building, that thing authenticates you. You may have some security person checking you in, and once you're inside, you go to the SCADA computer, and what we've seen many times is there's a little sticky note on with the username and the password. Everybody uses it. So in the old days, that was fine because people may not have been malicious. But nowadays, we've seen many examples of that being abused because you don't have the physical access. You're not that air-gapped anymore. And even air-gap systems, like isn't that secure. We saw that with Stuxnet, or that's the one that most of us became aware of the issue. So a lot has changed, and COVID definitely accelerated this need for a more secure way of handling our OT information.
Tell me a little bit about the HMI part of it.
It may be a visual representation, and maybe that's also part of the issue. Initially, the supervisory part is the important one. I subscribe to a control narrative that says you've got autonomous real-time control with cloud augmentation. So if there's no internet connection, if everything else fails, the system has to be autonomous and should be able to work by itself. And then tag onto that a lot of the stuff that's been done with CE from Idaho National Lab, the consequence-driven cyber-informed engineering. If you design your system like that, it will always be autonomous and it will work fine in most environments. So talking about the HMI, a lot of cases, the HMI should just display what's happening with your plant. So, and allow users to interact, to change, say, some set points. So if I want, in our world, if I want to change my tank level from 15 feet to 16 feet, that interaction happens on the SCADA system and the associated HMI. You also get local HMIs that can sit on the individual devices, and they mostly used informatively or maybe to override the running of a system. But what we also see, the SCADA system was used to collect information and store that in a historian. And as we've seen with a lot of the AI companies recently, there's no shortage of AI algorithms. There's a big shortage of data. So all of a sudden, people say, if I can just get access to the data, and then they discover it is not as easy as just interrogating a database, because it is on this historian. And now we perpetuate the issue, right? Because now you get people that have nothing to do with the running of the plant getting access to the heart of the system because they need the data from the historian. And unless you architect the whole thing correctly, the IT folks now trying to do data analytics or big data or just run some AI algorithm on the data also get access, and you just increase your security footprint or the lack of good access and security controls.
So what was the initial problem and how did you come upon it?
So when we started the company, what we did was create our own ASICs that understood all the electrical signals used in process control. So we built essentially at the time what was the replacement for PLCs. And that was a good 15 years or so ago. And then quickly I realized that it becomes a commodity, right? When you sell hardware, you have to compete against the big guys. It becomes a commodity and you lose because people will just squeeze you on price. And then what I would like to see is what's the aggregates and the critical KPIs of my system. So connecting these devices to the cloud or to at least the database was just an obvious next step. Also comes from some of the previous work that I've done. And then I started looking at what is available, like the old protocols, Modbus and the like. And obviously they're extremely insecure. So we thought we can do it better. That's where the idea was born to do our cloud service. The next step in the evolution was, so now that we have something where you can measure and control and do a lot of things with people's actuators and sensors, what's the next step? So the next step is this visualization and allowing essentially a SCADA system, because people don't want to pay the amount of money for a SCADA system just to control small installations. So our search for a market was was rather difficult in the beginning, because if you can do everything, what do you do, right? Then we started looking at water systems, and specifically small water systems, because they can benefit the most from automation, but they can afford it the least. And that's how we got involved in the water space. And then the next step in the evolution is, wouldn't it be nice to have a cloud SCADA system? So around 14 years ago, we launched our first cloud SCADA system. Subsequent to that, we now have more than 200 customers using us for all kinds of things in water, wastewater space, and also in composting, and a couple of other places where OT is prevalent. So that's pretty much the history. Initially started because small water systems were accessible. And now we're in this place where a lot of your podcasts also talk about the issues that small water systems face with security, and not necessarily small ones, pretty much the big ones as well, because you still have these constraints of the old architectures that people are tied to.
Okay, that does make sense. So when we talked about air gap systems, we assumed security, where, as you said, you had the authentication to get into the building. You had all this stuff that was physically built, and now we're starting to abstract it. Now we're starting to automate it. So we need to provide security for those.
We don't provide security per se. We provide a better way of working in a very hostile environment. And what I mean with that is, my wife loves gardening, and we had a big issue with deer because our backyard faces open space. So after a lot of trying everything, like putting soap on the leaves and everything, nothing worked. I raised our fence by 2 feet. Now my neighbor has the issue. We don't have an issue with deer anymore. So I think there are a lot of common sense things that I see in cybersecurity that will at least take out the opportunistic people trying just to figure out if there's a hole in your system. And to that end, what I see a lot is default configurations. And by changing the way that default configurations are used, you can dramatically improve just general security. For example, is many companies have a policy of multi-factor authentication, right? Make the default, you have to do it. And if you want to override it, then you can disable it. What we've seen a lot in the past, at least, is you can enable multi-factor authentication, but it's not the default. Same thing with embedded devices. If you send that out, is in the past, they used to all share the same username and password. Now, at least California law requires you to have unique usernames and passwords. It's just common sense things. And like the one quote said, common sense ain't that common. People just don't do the right things.
Earlier, we discussed the value of data.
The concept of value of your data is important, because SCADA in itself promises so much, but actually the use is reduced to an operator, right? And it's a very, very important use, don't get me wrong. But then when you get beyond just the operator, you can start thinking about optimization. Because coming back to an operator's perspective is, if my tank is low, I'm going to make sure it runs. If it's high enough, I'll stop it. And that's it. But if you go beyond that and analyze the data, like a lot of people do with AI nowadays, you can say, oh, I can optimize for cost. One, that's when the electricity is cheap. Or I can choose to optimize for greenhouse contributions, right? So I'll much rather pump when there's renewable energy available, but having access to the data now goes beyond how it's typically used in a SCADA system, because the SCADA systems are often implemented just for the operator. And then if you go beyond that, you get to the place where you've got autonomy. So we start with the monitoring, then we add the control. That's the SCADA realm. We start looking at optimization, and then we get to autonomy. Because in the IT world, people love analyzing data and say, oh, it would have been fantastic if yesterday you ran your whatever between this and then. It's not useful at all, right? Unless you can make it actionable. So by changing that around, that value is to say, from this optimization, we can learn and we can actually provide complete autonomy of the system. That's where the value is. And that's where the differences are, I think, with IT and OT, because OT is, hey, man, if you didn't do it by now, it's done. You can't just do it and do the right things.
So you're basically increasing the visibility into the devices that are already out in the field.
We do. And maybe if we talk about the architecture, you've got greenfield, where we just install everything from scratch. Those are the easy ones. And even if you look at the traditional vendors, the security posture of most of these folks have improved dramatically over the last couple of years, just because of the need. So like the S7 PLCs that you've mentioned in some of your podcasts, they now have security. I cannot just go in and get the configuration. If I want external devices to communicate to those devices, I have to explicitly enable that. So big change from just a few years ago. So if we look at the brownfield, then that's where the issues are. So what we say is, if you have a parallel system that will also look at your network, then you have something that's much, much more secure. So picture a traditional site where you've got all your PLCs running your site, you've got your SCADA system, everything on-premise. Rather than having a duplicate on-premise system with another SCADA machine there, use a completely different architecture that will extract the information from the SCADA system, extract the information from the PLC, publish it to the cloud. Once it's in the cloud in a database, you've got different levels of access, because now you've got very secure systems with role-based permissions, authorization, authentication, and you can have really fancy alarms. Because what we've seen also in terms of security is, when you don't get an alarm, is it because there's nothing wrong with your system, or is it because your alarm system failed? You don't know. Whereas if you have a cloud service that's distributed over multiple geographical nodes, the one can watch the other one, at least you get a notification that says, I haven't received any communication. So by doing these things, if you have a cyber incident, regardless of what caused it or if it was set up correctly, at least you will know something may be wrong, and then you can go on site and run your system in hand mode if you need to. So what we focus on is this data platform. The data platform has a lot of things to enhance security, like alarms, like the watcher watching the watcher type of thing. So a strong architecture of that, and then having secure different channels into it so that the multiple users of the data can use their data. So the operator will have a SCADA interface, and then people doing data science need what they, or get what they want to get, and folks doing the regulatory compliance and filings, that they have a different access. But what you do is you break the access to the heart of your SCADA system, and by that you reduce your attack vector.
So it's kind of an event viewer.
It can be, but it's way more than that. So initially it's all about the data. Once you get the data, you can have all these, call it equivalent of apps, sitting on the system. And one of the apps may be a data viewer. Maybe one looks pretty much exactly like a traditional SCADA system. Or another app is, I want a fancy graph that I want to publish to my board. But the difference is it sounds a lot like IT stuff, like what people do with Tableau and the rest of it. But it was designed specifically for OT environments. Whereas, as you know, is when we have data breaches like Experian, it's annoying because these people should know better, right? And it's expensive, and but it's not that bad on one level. If we have a breach in a water system, the consequence, or in any other OT environment, the consequences may be significant because people can lose their lives. So the consequences of something bad happen is just so much worse in the environment that we work. So our design focus is on that level, making sure that the stuff is secure.
So we've talked a lot about water districts. Water is a part of this, but does it map over into other OT environments?
Absolutely, because when you look at most OT environments, there's a lot of commonality. If you reduce everything to the base level, is you've got sensors, you've got actuators, and you've got controllers. So pretty much everything mapped to those three primitive devices. And then you get the specifics for the market. So in a water system, it's all about actuating, starting to run the pump until a sensor says the tank is full and you shut down the pump. The controller says, oh, it exceeds some level, I'm shutting it down. If you look at oil and gas, you've got a sensor measuring something somewhere, and if some value gets exceeded, you perform an action. And even my Nest thermostat, same thing, right? If the temperature drops below what it's supposed to be, it actuates the furnace, and my home heats up until a certain point and it switches off. So those primitives are all the same. Now, the specifics, that's a little bit different. But what we see more and more is you've got vendor controls in the devices. So your control that you do is on a much higher level, and they take care of all the details. So think about pressurizing a water system. You just tell the thing, I need a certain pressure. The vendor will make sure that everything happens. So our job, so your question about mapping it to different industries, yeah, it's very similar. It's all time series data. The way you present it may be different, maybe a different type of graph, or maybe a different primitive to show this is a bottling plant or something else, but the underlying data, exactly the same thing.
So back to the water districts. As you're talking about potential customers and so forth, are you finding that water districts are not automated at all, and they're still just using the old systems?
Relative, right? Not automated at all is maybe taking it too far, but very primitive. So we see float switches sitting in a tank, and then when it's this thing hanging on a piece of cable, and then gravity or the water pushes it up, the pump stops. When it falls down, the pump starts. So that's the level of automation that is all over the place. And the context here is in California, there are 7,500 or more water systems. 7,500. You never knew that, right? Because you see San Francisco and maybe East Bay Mud and a couple of other ones. Those are the ones that we know. But there are so many small mutual water companies where they just don't have the resources.
So wait, they're still using literal floaters to tell them the exact measurements that they need? Are they just cash strapped, or is that something that's always worked and they continue to use it?
Both, but resources is a key thing here, right? Because if you think about Marin County where we live, there are two large water companies. San Francisco, there's a big one on the other side of the bridge, a big one. So the customer base of these are big enough to support everything that you can imagine, and cybersecurity professionals, all of that. The small guys don't have the customer base. One of our customers have 8 hookups. It's in San Jose, So you would think they would get it from the city, but it's a small entity wanting to do their own thing. So they just don't have the resources. And that's an interesting dynamic that we see in the water industry in general, is a lot of the people with the gray hair like me are retiring out of the system and very few people to replace them. So what do you do to collect the years of knowledge of these people? And that's where the cloud also becomes very, very efficient, because the workflow in doing a traditional automation system is so different. You've got all these different touch points, somebody designing the control narrative, somebody implementing it on a PLC, somebody doing the design for the SCADA system, implementing it. And with the cloud, all these things are templated, right? So anybody can interact with them. So we can get that collective knowledge and expose that to the user. Or to the user base in a way that is affordable to them.
So when we've talked about water, we've talked about initially turning on the faucet and having it in your home. But you have other uses of water, of course. There's agriculture. So irrigation systems, can they be thought of as SCADA?
They're very SCADA intensive too, because you've got some of our customers, large irrigation suppliers, they've got gates that they want to control. They want to see who takes what water when. People can subscribe automatically to have, say, a quarter of an acre feet delivered tomorrow between 8 and 12. And they need SCADA systems for that, because they also want to optimize their operations, right? So if you can pump when the electricity is cheap, why wouldn't you? So by having the flexibility of the cloud that says we can go and read PG&E's rate structure, and we know it's going to be more expensive from 4 to 9. So therefore, we can calculate how much or what time we have to start the pump so that by 4 o'clock, the tanks are full. Those are the type of flexibilities that you get in the cloud. But I think those are just some of the benefits. The core is this thing about disasters, right? It's not a matter of if, it is when. And I found this very interesting illustration in a technical book. So disasters will happen, and at some point in front of the disaster, there's your most recent backup point. On the other side, there's a recovery point. Between the two, there's data loss and downtime. So you've got a couple of questions to ask. The one is, how much data can you afford to lose? And the other one is, how quickly must you recover, or what's the cost of downtime? So the cost of downtime, we've talked about that, is you have to run the plant manually. So you have to have people on site 24/7. That's the cost of your downtime. Data loss is, suppose I've got an on-premise SCADA system. That computer failed because, it's still running Windows XP. Now I have to go and get another computer, get a new operating system, get a new version of the SCADA application, and then I discover it doesn't work because I don't have the right license. So you've got a tremendous amount of potential data loss that you have there. But compare that to the cloud. We practice for disasters. The first time when we practiced taking the system down completely and restored it, it took us in a controlled environment more than 30 minutes to do it. We were down to 5 minutes to start from scratch, from nothing, to redeploy our system. But we don't have to do that because we've already automated it. And the last catastrophic hardware failure we had less than 2 minutes of customer service, people trying to log onto the system, less than 2 minutes. So over a 14-year time span, we're at about 90 minutes of access lost to the system. And I think that is significant, is to say, because I'm convinced that if a nation state with all the resources and all the smart people that are way smarter than we are want to break into your system, they will. There's nothing you can do to stop them. And by approaching it that way is to say, how can we shrink that data loss? How can we shrink that downtime? You're in a much better position. And I think this is something that cannot be overemphasized is people have a false sense of security when they make backups. Mm-hmm. If you haven't restored a backup, you don't have a backup. You have to make sure that that thing works. I love photography, and I'm diligent in backing up everything. And at a time, I used Windows machines and used some third-party software to back up my pictures, and my Windows machine failed. The new version of Windows, the vendor doesn't exist anymore. I know my pictures are on that disk. I cannot get access to them because I've never practiced this thing of restoring my information. So I think in this world of cybersecurity is, following all the guidelines is extremely useful, but it's very wise to practice a day without SCADA and then to practice restoring your backups so that you make sure that what you have is or what you think you have is actually useful.
So you touched upon something very interesting. Recently in Kansas City, Kansas, there was a water district that was impacted with a potential cyber attack, and they switched over to manual while they ferreted out what was the actual problem. So having a system that's in the cloud, to your point, if that goes down, are you continuing to work with the companies to provide manual?
It's not regulated, it's implied, right? Mm-hmm. So if you look at the American Water Infrastructure Act of 2018, they talk about a system's ability to adapt or withstand the effects of unusual incidents. And if it doesn't happen, it also, the language is to rapidly return to normal operational conditions. So the regulation is implied, it's not enforced. So some of the things that we've seen engineering companies do is to do this thing, practice a day without SCADA. Because what we know is it's not a matter of if there will be attacks or something bad happen. It is just a matter of when. So if you say incidents are more general than just cyber incidents, and you prepare for that, you will also be prepared for cyber events.
Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. I've got some great episodes coming up, including more on hacking water facilities. Subscribe today. I don't want you to miss out.